Section 4.3, we're going to expand what we did in Section 4.2. In 4.2, we looked at something called relative extrema. And relative extrema is this idea that when you've got a grouping of something, in this case we're looking at a graph, in a nearby area, it is the largest value or the smallest value in that nearby area. Okay? That's what relative extrema is. Now with absolute extrema is the idea that it is the absolute largest value or smallest value. It's not about the local area, it's about the entire graph or the graph on a specific set of intervals, which is usually what we're looking at. So the absolute extrema looks something like this. Let me draw a picture for us. Come on. Okay, this graph I'm drawing, it starts here and it ends here. It's just got a starting and a stopping point that are clearly defined. Now, when we looked at the relative extrema in the last section, we would have said these locations are relative extreme values, right? The peaks and the valleys. So we would call the first one a relative minimum, and we would have called the second one, you know what, let me change my graph just a little bit so that I can describe something differently. Let's actually stop our graph right there, okay? So please change that from what you already drew. My apologies. Okay, this one would have been a relative maximum. If you haven't already, please go back and listen to 4.2 so that you know what I'm talking about, because I'm assuming right now that you've seen it, that you know what I'm talking about when I talk about relative extrema, okay? Now, obviously, that relative maximum that I circled is not the absolute biggest y value on this graph, right? Where's the bigger value than that one? Where is a bigger value than that one? Yeah, the starting point, the far left-hand side, right? This location and this location have a name. We usually call them the end points. It's the starting end and the terminal end, or the ending value. They're the end points of our graph. And they are also locations where we might have the biggest or the smallest value. They don't have to be, but they could be. And on this one really is the absolute maximum, right? The far left-hand point on this graph is my absolute max. Wouldn't have to be, but it is on this graph. Now, the far right-hand endpoint, it's a potential minimum, right? But it's not the absolute minimum. Where's the absolute minimum on this graph? It's the same as the relative minimum, right? On this one, this is also the absolute minimum. So this would be like the idea, and I didn't give this as an example because I always like to do this in class. In my family, I'm tall. And I'm not joking. I am 5'4". 5'4". Every woman in my family is shorter than me. Every single one. Okay? Now, I'm pretty sure that every single young man in this class stands up, and I am not tall. Is that true? Every time you guys do group work, I feel a little intimidated because you guys are just towering above me. My son and my husband, they tower above me as well. Okay? In my husband's family, the one that we just went on this trip with, there's one other woman, two other women who are the same height as me, or very, very close. And every other woman is very tall. In fact, there was one point when I had a sister-in-law who was almost 6 foot. She didn't shrink. She's just not my sister-in-law anymore, to clarify. But yeah, so in my husband's family, I'm not tall, right? It's who you're comparing me to, correct? Also remember being when my husband was a youth pastor up in Ohio, and my mom came to visit us, and she's convinced that I'm tall, and all of a sudden she realized that amongst all the youth, like junior high and high school kids, they were all taller than me as well. It's like an earth-shattering moment when my mom realizes I'm not tall. Okay, so that's the relative extrema idea. But the absolute extrema idea is when somebody says, like, no, they really, really are tall, right? Like, young men in this class, you guys are tall. Okay, you're tall. But if you go to a Thunder basketball game, that's something different, isn't it? You go down on that court and you meet Russell Westbrook and you are no longer tall. Yes? Yeah. Right? I mean, and then also, if all of you went and you visited the first grade classroom down the road at Jefferson Elementary or Will Rogers, you would no longer be short. So if you want to feel tall, hang out with the little kids, right? Same thing. It's about what really is the case when you're considering a much larger context. So when we're finding extrema in this broader sense of absolute extrema, the first thing we're going to do is going to look a lot like what we did in section 4.2. We're going to find the places where we do have derivatives that are zero or the derivatives don't exist. And what we're looking for in this case is we're looking for those places of potentially relative extreme values. Okay, now these don't always give us relative extrema, but they're a good place to look. Okay, they're a good starting spot. So the first thing we're going to do is we're going to look for the places where our derivative is zero or it doesn't exist. The second step is that we're going to examine a graph to determine which one's a maximum or minimum. Right? You have a calculator. We use the calculator pretty intensively in this class. When we get into section 4.4, we're going to use it even more so. I'm going to show you some cool things I haven't shown you yet about derivatives, and you're going to be like, whoa, that would have been nice to know before now. And you're going to be excited, I hope. So, third step, though, is then to test the end points. This is probably the place where people forget, forget step 3. If they're going to forget something, they're usually forgetting step 3. You're going to test the end points. You need to see if the locations on the end happen to give you a larger value or a smaller value than what you already found. Okay? Yes?
Do you have to have endpoints to have an absolute?
You don't have to. There are some graphs that will have absolute extrema without endpoints. Think about like a parabola, right? It would have an absolute maximum or minimum, but it wouldn't have both. If you think about graphs that are like trig functions, like sine and cosine, those have lots of absolute max and minimums, and they don't need to be bounded at all. Most of the ones we look at are going to be bounded, though. And in terms of a business context, when you're thinking about things, the bounding makes sense. Usually the creation of these equations are dependent upon a particular time interval. Like the company didn't start at negative infinity, it started in 1952. So there is a definite starting point. And at some point the company either ceases to make a profit, in which case we stop looking at the data, or we're caught up to current and we have to stop looking at the data. So a bounding process makes a lot of sense in a business context. So most of ours will have those endpoints. All right, so we're going to do a couple examples. This one does not have context with it. It's very basic. Polynomial that you absolutely know how to do, right? You know how to find this derivative. So the first step here is to find the values where the derivative equals 0.
We don't have that.
We don't have that.
Yeah.
Okay, what's the problem that you have? I'll fix it.
X equals.
Oh yeah, it is on my page too. I don't know. Copy pasting sometimes isn't helpful. Let me fix it. Okay, so let's do f of x equals, you've got 0.04 x cubed minus 0.88 x squared plus 4.81 x plus 12.11. Does that look okay? You've seen that function before? Yeah. Okay, fabulous. Okay, so it's starting out with finding relative extrema. Still no context on this particular problem. So the way that we find relative extrema, this is from 4.2, this is where we're starting it, is that we're going to take the derivative and we're going to set it equal to 0. So we're going to take the derivative by hand. It's not a hard one to take the derivative of. So you're going to bring the 3 down and you're going to multiply it so you get 0.12x squared minus 0.88, nope, I'm sorry, 1.76 x plus 4.81. Does that look right? And we want to set this equal to 0. So grab your calculator. And I want you to plug in that equation into y1. And you know what? This is a fantastic time to show you, actually. I won't even wait till 4.4. I'll show you the cool trick. You ready for the cool trick? It's going to blow your mind. You're going to be like, wow. Okay, so grab your calculator. First of all, go ahead and put the derivative into y1. And let's just look at a standard window because I'm not sure what else to do at this point. We're just going to do zoom 6. What we're really wanting to find in this graph is what? What are we looking for? We're looking for zeros, okay? Because we're looking where this derivative that we have found equals 0. So we're looking for the place where it crosses the x-axis. Remember, we can do that one of two ways. You can actually do second calc, and you can do number 2, 0. You left bound, right bound, and so forth. If you don't like that option, you can let y2 equal 0 and look for where it intersects, and that's fine too, okay? Either way is fine. I'll do the 0 process as a 0. If you'll notice, though, as we graphed this, there's one of the answers that's off my screen, so I'm going to make my window just a little bit bigger. So I'm going to make my window go out to, say, 15 and see if that's far enough. And it is. So I've got the two places where it is crossing the x-axis. So I'm going to do second calc, 0. Left bound means I need to be on the left-hand side, which I am. Right bound means on the right-hand side. Now I am. And then guessing, which is the location somewhere in between. So one of my solutions is x equals 3.633. And we're going to find the other one. So we're going to do second calc, 0. Left bound, I need to be on the left-hand side of the second x-intercept. Right bound, on the right-hand side. And then guess, we're going to be close to it in between. And the second value is at 11.034. Okay, so a couple things that are kind of cool about this. We put this into y1. I want us to go back, and I want in y2 for you to put the original equation. Okay? Now I know you did this on your homework, where you graphed two graphs at the same time. Sometimes they're in a good window to see both of them, and sometimes they're not. I'm not concerned about the window showing both graphs right now, so I don't really care to manipulate that, but I am going to put the other equation, the original one, in. We could have put it in y1 and then the other one in y2. It doesn't matter which one they're in, though. Okay. So this is really a terrible graph window for both of them, right? I can't see the other one at all. But I don't really want to see the other one. So let me show you how you can deal with it. We're going to do that process again where I did the 0, okay? You're going to make sure you're on the right equation for doing it, which I still am. Left-hand side, left bound, right bound, and the 0 in between, okay? There's the same thing I had before, 3.633. Everybody good with that? Got the same answer you did before. Just hit the up arrow or the down arrow. Up or down, I don't care which one. Do you see the equation name at the top of your screen or the bottom of your screen? What equation am I on? I'm on the original equation, the one that I just had you put in y2, right? It says y2 0.04x. Here's that same x value, 3.633. That's the y value that goes with it. That's cool stuff, because you don't have to enter it by hand. And what's even better is that it's the exact expression. It's not 3.633 that's plugged in. It's 3.6327328, ... which means it's more accurate. So the y value that goes along with 3.633 is actually 19.888. Yep. I'm going to do it on the other one. Yeah, so I'm going to do it on the other equation. So go ahead and write down that the y value that goes with that is 19.888. So we'll try the process again. We're going to do second calc. We're looking for the 0. It says left bound. I'm going to try to find this location right here, so I'm going to move over closer to that value on its left side. It says right bound, so I'm going to arrow over to the right-hand side of that one and press enter. Guess means that I need to be close to the actual x-intercept. There's the 11.034 that I got a minute ago. Yep. And if I hit either the up arrow or the down arrow, depending on what equation I've put that into, I can find the correct y value in the original equation, and it should be 11.779. Okay, so that's only the tiny bit of blow your mind. Are you ready to see something even cooler? Okay, I want you to hit y equals and just clear out what's in your calculator right now. And I want you to put your original equation in y1. Okay, everybody just put your original equation in y1. So that was 0.04 x to the third minus 0.88 x squared plus 4.81 x plus 12.11. And when we started this problem, I made the comment, this is an easy equation to take a derivative of. And it is, right? It's just a polynomial, nothing really complicated. But there will come a point when we're going to put something in where we have a table, and we create an equation, and it gives us like the long slew of decimals, correct? And we're all aware that at the point when we stop writing down the decimals, it changes the accuracy of our answers, right? So it would be nice if we could get the accurate answer and not an approximation when those kinds of things happen. So we're going to let our calculator find the derivative for us. It won't give us an equation, but it will give us a graph. So let me show you. Go down into y2. And I want you to press the button that says Math. It's on the left-hand side of your screen, Math. Now there's a lot of little different things here, fractions and decimals. There's cubes and cube roots, and maybe you've used some of those before, maybe not. But if you scroll down to number 8, what does it say? In deriv. Now, some of your calculators give you some notation that looks a little different, probably, does it? Does somebody's calculator look different than in deriv? No? Okay, it might when I hit enter. So on number 8, I want you to hit enter. My calculator actually plugs in the word in deriv. Does anybody else's calculator do something different? Okay, I'm going to borrow yours, Hannah, so you can see the other options. Okay. Yours looks like one of these two, I believe. Okay, Hannah's is a little bit brighter screen than mine. Let me see if I can back out if it will help. That's not too bad. Okay, so does everybody's screen look like one of these two calculator screens? We're good? Okay, if yours looks like mine, this one where it says in deriv, I want you to follow the keystrokes that I do next. If yours looks like Hannah's, just hold tight and I'll show you what to do next, okay? So on mine, what we're going to do and tell our calculator is that we need the equation that's in y1. Because we don't want to type it all in again. That's just time consuming. That forces us to stop decimal expansions, things like that. We want it to do it without actually having to type much in. The way that you get that is you hit this button that says vars. What do you think vars is? Don't everybody answer all at once. Variables. That's what you were thinking. You just didn't want to answer. Variables. Hit vars. We're going to go over to where it says y vars. So arrow to the right at the top. See it says y vars? Vars, but it's vars because variables. I don't know, whatever you want to say. Y vars. Vars, y vars. All right. Number 1, function. We're working with functions. And there's y1. So what we have now told our calculator is we want to take the derivative of the equation that's in y1. Okay? So this is my language on top of the calculator's programming language that you're hearing. The next thing you need to do is put a comma. And then you have to tell it what the variable is. Well, what's the variable in y1's equation? What is the variable that's using? X. So we put an x. Then we do another comma. Whoops, not a square, a comma. So now we've said we want the equation y1, the derivative of that with respect to x. The next, with x as the variable. Then you're going to put a comma and another x, okay? This is saying for all x values. I don't just want it at, say, 4. I want it at every x value in the whole string. So jot this down. This is your notation. In deriv, parenthesis, y1, comma, x, comma, x. Now I'm going to hit graph because I want you to see that this actually looks exactly like what I just deleted out a minute ago. There's that first function going up in the middle of nowhere. And then there's my second parabola that we just found all of the calculations at. Okay? And you can do all the same steps that you did before where you're finding the roots and so forth. Now let's look at Hannah's because it's very similar. It just puts things in different places. You'll notice that this notation over here looks like, in fact I'm going to move this screen so that it gives me a better coloring. Looks like one of the notations that you've seen before with derivatives. D blank. Well, it's an x down here because it's the derivative with respect to x. X is your variable. The next piece you're going to put in is the name of the equation. That was y1. So you get that by hitting vars, y-vars, function, y1. Derivative with respect to x of the function y1. And then over here, this is where we'd normally see a number like x equals 10 or something like that. We don't want that. We want it to do it for all x values. So we're just going to say x equals x, which I know that sounds kind of silly, but that's how we tell our calculator that we want it for all the x's. And if I hit graph, we see the same graphs that we saw before. It does take the calculator longer to draw these. If you're working with a logistic function, sometimes it takes it like almost a minute, which sounds like forever when you're talking about technology these days, right? That's really slow. But it will take it a little bit longer. Okay? All right. I think we should probably finish the problem, which we didn't. We just sort of took a technology aside. But let me give this back to Hannah. Okay, so we found the xy pairs 3.633 along with y is 19.888 and then x equals 11.034 at the y value 11.779. Okay? The thing that we're supposed to do though is we're supposed to find the relative extrema, and finding them means saying which one's which. Which one's a max, which one's a min. If you go back to your calculator, if you want, you can clear out y2. It doesn't need to be in there. But we do need to look at the original equation to see what happened and see which one really gave us a maximum and which one really gave us a minimum. Try again. So I don't really need the end deriv, so I'm going to delete mine out. And my window here was fine on the x values, but the y values needed to go higher. You can either manipulate the y value max to be higher, or you can hit zoom 0, which is a zoom fit, and it will automatically be higher. This isn't a super great window, but you can see right here that there's a maximum right there on the first one, and then it dips down just a little bit to give you a minimum over here. So that x equals 3-point number is the max, and the 11-point number is the min.
But isn't that the relative min?
It is. That's all we were asked to do for the first equation, or first part. Part A said relative minimum and maximum.
Oh, extrema.
Yes, extrema means minimum or maximum. It's just a word that encompasses both. Yes.
In the 452 notes, you also did the number line thing. Is that okay?
You can do the number line as well, absolutely. So if you do the number line, the way that that looks, Brooke, just since you mentioned that it's a good thing to ask, is taking the 3.633 and 034, and testing numbers in between. So if you test a number on the left, maybe you decide, I'm going to test the number 0 because 0 is a friendly number. And maybe you test a point in between, you're like, okay, 5 looks good, and a test a point bigger, and you're like, okay, how about 12? And you plug them into the derivative. If you do that, you'll end up finding that this is a positive value, so it's increasing, a negative value, so it's decreasing, and another positive value, which gives you a max here and a minimum here. So, okay, I have way too much written on my screen and too much space. Let me move this guy. So I had the point 3.633, 19.888, and this one is a maximum, relative maximum, like Lainey pointed out. And then the other one, 11.034, 11.779, and this one is a relative minimum. That's part A, the relative extrema. Part B says find the absolute extrema. So when you have the absolute extrema, you're halfway there because you already found the relative extrema, and that was step 1 back over here anyway, right? Find the relative extrema. So when you're taking a look at these, you already have sort of 2 points as contenders. These are contenders as long as they're right in the interval between 0 and 16, and they are, right? X was 3 and 11. So these are contenders for being the absolute extrema. So one of your options is you've got 3.633 633, comma 19.888. You have 11.034, comma 11.779. But you're also supposed to test the endpoints, namely 0 and 16. So we're going to take the 0 and plug it into the original equation and find out what's the y value. And in fact, our calculator still has the original equation in it, so we can use the table in our calculator to do that. So if I go into my table, I can put in 0 because that's one of my endpoints, 16 because that's my other endpoint. So at 0, my y value is 12 point, let me go over to it, yep, 11, or 1, 1. And then my 16, I have 27.63. So now what we're doing is a comparison among all the y values. Now this doesn't work for relative extrema. You can't test relative extrema this way, because sometimes the relative maximum is smaller than the relative minimum. Right? My son's class in school, he's the tallest. My son in my family, he's the shortest. Doesn't work like that. It's what it's compared to. So you can't do this process for relative extrema, but you can for absolute extrema. You have 4 y values. Which one's the smallest?
11.
The 11.779. This one is my smallest, so this one is my absolute minimum. Of my 4 y values, which one is my largest? Oh, I'm sorry, I'm not displaying. No wonder you guys are like, I don't know what she's doing. Which one is my largest? The 27.63. So this one is my absolute maximum. So when it asks me find the absolute extrema, the absolute minimum, if you will, is the point 11.034, comma 11.779, and the absolute maximum is 16, comma 27.63. It's a comparison at that point. The biggest one's the absolute max, the smallest one's the absolute min. Okay? All right, we're going to do one with some context now. This one says, suppose the flow rate in cubic feet per second, which is CFS, of a river in the first 11 hours after the beginning of a severe thunderstorm can be modeled by this equation. CFS, that's the cubic feet per second, H hours after the storm began. First question, part A, what were the flow rates for H equals 0 and H equals 11? What is this question asking me to do? It's the original one. This one isn't the derivative yet. Because it's not asking me how things are changing, it's actually asking me what the flow rates are. And I know that's tricky because they use the word rate here, but this is actually an equation for flow rate. So on this one, they're just asking me for the equation's value at H equals 0 and H equal 11. So we're going to find F of 0 and F of 11. If you take your calculator, we can use our calculator to do that. So change your equation in your calculator to represent negative 0.86 x to the third plus 12.05 x squared minus 8.95 x plus 123.02. You can go into your table and you can plug in 0 and 11. Now, one of the things to be careful of when you're plugging in values is that it looks like both of these are 123.02 and only has 2 decimals. And it may only have 2 decimals, but you should go over an arrow on top of it to make sure. So if I'm on top of that, it's highlighted at the bottom, it'll show me all the decimals that really exist. Because if it has 3, we're going to write 3 down. Okay, this one doesn't, so that's fine. On the second one, same thing, it's only 2 decimals long. So F of 0 on this one is actually 123.02, and F of 11 is 337.96. Okay, now some of you are still having some difficulty remembering to write units on everything. So this is the context problem. It's got units, so the answers are going to be having units too. What are the units on this answer? Are these two answers? CFS. Okay, CFS. All right, part B. Part B actually asks us now to find the absolute extrema on the interval. So this is like it jumped through, like the last problem, it sort of guided me through it because it said find the relative extrema and then it said find the absolute extrema, right? And this one just jumped full gun to the end of the problem. But that doesn't mean you don't have to do the relative part. You still have to find the relative extrema to answer the question, whether it asked for it or not. Okay? So we need to find where the derivative equals 0, but here's the catch. It didn't actually say find the derivative, right? And if it didn't actually say find the derivative, then we don't actually have to show that we found the derivative, which means that our calculator could be quite useful in using nderiv like we did on the last problem. So we're going to do it that way. So you're going to take your calculator, go to y equals, and we're going to practice this. Down in y2, for practice purposes, we're going to tell it to do math 8. In some version in there, you're going to tell it the equation is y1, the variable is x, and you want to do this for all x values. So in my screen, that looks like vars, y vars function y1, comma x, comma x. If yours looked like Hannah's did, that means you're going to have a d over dx, y1, x equals x. Now, you do know that your window really doesn't need to look at anything beyond 0 and 11, because the flow rates started at 0 and it ended at 11, and the equation actually told you this is only, this equation is only good, it's only accurate for the first 11 hours after the storm. So 0 and 11 are the natural endpoints on this problem. Now I don't know what my y min and my y max need to be, but I do know that I'm trying to look at what happens around the x-axis, right? I'm trying to find where the derivative crosses the x-axis. So I need to make sure that the minimum is negative and the maximum is positive. And it probably doesn't even need to be as extreme as it is, so I'm just going to go negative 10 to 10. And if it doesn't look good, we'll manipulate it, okay? So I'm going to graph it and let's see what happens. Now it's going to graph the first equation first. Do I care about the first equation right now? I really don't. I really only care what happens in the second equation and where it crosses the x-axis. And is it crossing the x-axis in this screen? Is it? I have an equation crossing the x-axis, don't I? Does yours? If you don't like this picture, you can manipulate it so you can see a higher value and a lower value. So if you want your y max to go higher, I made mine 50. This is the derivative graph that's graphing right now. If you aren't sure, you can trace it to see. If you hit trace, you can see I'm at y1. I don't see anything, but if I arrow down, there it says y2, and you can see my dot at the top of the screen. Can you kind of see that? That equation where it looks like the parabola, if I arrow right and left, you can see it. On the top, it tells me that I'm on y2, nderiv, y1, comma, x. I'm on the derivative equation. So this curve that we're seeing cross here and cross here is my derivative equation crossing the y-axis, the x-axis, excuse me. Okay, so we need to figure out where it's doing that. So we're going to do second calc, 0. I want to arrow over to the left. I can't see it almost because I've got so much words all over my screen. But if you follow the x value down here, you'll see you're at x equals 3 and your y value is still positive. Do you see this? Oh, I need to be on y2, sorry. There is my y2. There's my dot. X value is 3.27, y value is 44, and it's 39, and it's going down. And what I want is I want my y value to be negative because that means I will have crossed underneath the x-axis. And there I am. I'm at y equals negative 3.45. If yours doesn't say negative 3.45, doesn't matter. If it says negative, you're good to go. That's the left bound. Arrow to the right until your y value is positive. That would be a right bound. And then just be somewhere in between the two for your guess. The first x-intercept on the derivative graph is at 0.387. So on my iPad screen right now, I'm going to write down that x value, 0.387. I know that the derivative value here is 0, right? That's how I found this. I found where the derivative, y2, right, equals 0. If I hit the up arrow, it will jump up into the y1 equation. And then not only do I have the right x value, but it tells me the y value that goes along with it in the original equation, 121.311. And this is one contender for a relative, not a relative, but a one contender for my absolute extreme value, 1. Now, I have another contender over here on the far right-hand side. So I want to find this one. So I'm going to do second calc, 0. This tells me I'm on my y1 graph. I want to be on my y2 graph. And I need to be on the left-hand side. So I'm just going to arrow over until I'm getting close to the x-intercept, but still on the left-hand side of it. So on this particular location, if I'm close to the x-intercept, but I'm on the right-hand side, I'm still above the y-axis. I said y, and I meant x. I'm still above the x-axis, right? This point right here is still on the left-hand side of the intercept, and it's above the x-axis. I'm going to hit enter because it said left bound. I'm on the left. Now it says right bound. I need to arrow until I'm on the right-hand side of the x-intercept, which puts me actually beneath the axis on this one. You can hit enter, and guess means somewhere in between. The x-intercept is 8.954. So that's my x value for this contender, 8.954. And if I arrow up, it'll bump me back up into the y1 graph, and the y value is 391.604. Those are the potential relative extrema, which may also be absolute extrema. What other points do I need to test, though? Endpoints. And the endpoints on this equation are what x values? 0 and 11. And you know that because that actually was given to you in the problem. On part B, it actually says h equals 0, h equals 11. So we're going to do an endpoint at 0 and an endpoint at 11. And you can do that in your table by plugging in the 0 and 11 here. And if you're over here at y1, you can see it's 123.02 and 337.96, which is what we found on part A, right? We already did that for this problem. So I'll write them down on the screen at this point. 123.02 and 337.92. Now, I don't always have 4 points here. I might have 3, or I might have 2. I might have 6. I mean, I have plenty of options. It just depends on the equation. On this one, I had 4 contenders. There are 4 locations where I have either relative extrema or endpoints. I'll always have at least 2. If I've got endpoints, I've got 2 endpoints. I mean, like, that makes sense. And then any locations in between where the derivative is 0. There are 4 values here. What is the absolute smallest one? Yeah, this one at the top, right? This is my minimum, and it's the absolute minimum. Which one is the largest value of all of them? Yeah, it happens to be these 2 that we found first when we were looking at the roots. So when it says find the absolute extrema on the interval, these would be our answers for this particular problem. They happen to be the relative extreme points. They don't have to be, but they were on this problem. Yeah, they were the relatives, and they happen to also be the absolutes.